Okay, so today's speaker is Clémentine Prieur, and she's going to talk about goal-oriented error estimation for parameter-dependent nonlinear problems.
Okay, thank you. So thank you for the invitation. And the place is very nice. Everything is good. And so I'm going to present some work on goal-oriented error estimation for parameterized PDE. So Henry asked me to give a talk on parameterized PDE. So this is why I made this choice. And I will give some application to sensitivity analysis. And this is a joint work with colleagues in Grenoble, Maël Naudet, Alexandre Janon, and Clémentine Prieur. I first will give the toy examples on which I will illustrate the work. So the first example is classical in the literature. So it's the Venturi's example, where you have here a steady state incompressible flow which goes in a tube, and we have some unknown parameters which describe the geometry of the problem. So you have here three parameters: the height here, the width, and here that radius of geometry. And these parameters are only known by a game of variation. So we can consider that they are distributed as uniform on these intervals. Okay. And we define the state variable as the solution of that PDE. And so you have some Neumann-Dirichlet boundary conditions. So it just means that the fluid enters the geometry in that way with a unit velocity. And we are not interested in the whole solution, but on some quantity of interest, and it is the purpose of that talk. In that talk, we will consider that we have a reduced model for a PDE, but we want to get some probabilistic error bands on a specific quantity of interest, not on the whole solution. So here we consider that quantity of interest, which is just the mean and the boundary gamma n of a steady state. So the mean on that boundary.
Clémentine, you said this was a fluid flow problem, so is UE is like pressure or something?
Yes.
Pressure.
Okay, and we are interested in the influence of the geometry and that quantity of interest. Okay, so we consider the weak formulation of that problem, which writes as follows. And we then consider some Galerkin projection, and we want to solve this weak formulation on a smaller discretized space. Okay, so that we have our initial continuous problem, and we go to a discretized problem. And then I said we are interested in sensitivity analysis. So on this toy example, we want to know the influence of these parameters, geometric parameters, and the output of interest. And as I said, we have some knowledge on these parameters, but here the knowledge is limited. We just know that they are bounded in some intervals, so that we will model the uncertainty on these parameters by uniform distribution. And we assume also that the uncertainty and the different parameters are independent from each other. So here are other examples you could have some measure, so then you assume that the uncertainty is modeled by some Gaussian distribution whose expectation is the measure itself. Okay, and so now the output of interest is also a random variable as it is deduced from the parameters which are random. And then so what does sensitivity analysis say? So you want to know if you fix some parameter, how you reduce the variance of your quantity of interest. If you reduce that variance a lot by fixing the parameter, it means that the parameter is influent. So what do you want to do? You want to look at the variance of S of mu when mu I is fixed to some nominal value. But if you do that, it is local. You don't know how to choose that nominal value. And so as we have modeled the uncertainty with a random variable, we will use that ID and we will take the expectation of the conditional variance. So the conditional variance is a random variable, and we take its expectation. So this approach is called global sensitivity analysis, as we consider the reduction of the variance and the whole set of values that mu I can take. And then, usually what people do is that they use the total variance theorem, that is, the variance is decomposed in the variance of the conditional expectation plus the expectation of the conditional variance, so that they prefer to work, instead of the expectation of the conditional variance, they prefer to work with that quantity. And that quantity is always between 0 and 1. And that time, if you look here, I said if you fix mu I, if mu I is influent, then the variance reduces a lot. And now, as we take 1 minus this ratio, it is the opposite. That is, if the index is close to 1, it means that the parameter is influent. And if the SI, the ratio here, is close to 0, it means that the parameter has not so many influence of the output of interest. So it's the classical framework for global sensitivity analysis, variance-based global sensitivity analysis. Okay, and then we have several estimation procedures. If we know nothing about the model, we are in very big black box model, and we do not know any regularity, then usually people use Monte Carlo based estimation. But this estimation procedure is costful, even if we have some tricks to reduce the number of evaluations needed. It has some non-neglectable cost. And so it is possible, when using such a procedure, to get some confidence intervals. Okay, just classical confidence intervals, either by asymptotic statistics with a central limit theorem or using some bootstrap procedure. But if the output of interest is costly to evaluate, then we would like to go with a reduced model. And if we do that, so we do not consider a true output of interest, but S tilde of mu, which is defined as the output of interest computed on a reduced order model, then you have to take this error into account in your confidence interval. Okay, you have two errors. The error due to the estimation with the Monte Carlo procedure, so it is a sampling error, and then you have the error due to the reduced model. And it is possible to take this error into consideration, and once more, there exist several procedures, either with asymptotic statistics and an error on this quantity, or with a bootstrap procedure. But what we need to know is how we can bound this error between the true output of interest and the reduced output of interest. And it's the goal of the talk today. And in the title of my talk, I said that we were interested in nonlinear examples. So now I will give some nonlinear toy example we will use also in the simulations. So it's just an undiscussed Burger's equation with some initial condition and boundary condition. And the parameter here appear in the initial condition, alpha and beta, and they are assumed to be in 0, 1. And we do not work directly on the continuous system, but we will use some discretization scheme, and here we used discretization upwind scheme. So discretizing both in space and time. Okay. And then the last example will be a linear example on which we will consider some nonlinear output of interest. Because nonlinearity can appear in two contexts, either in the model itself or in the output of interest, or in both. And here we will consider a linear transport equation, and with only one parameter, which is uniformly distributed. And once more, we discretize that system, and we will use this space-time scheme, which is a first-order upwind implicit scheme. Okay. And then, so the full dimension of the problem is high because this calligraphical n is the product of the number of space steps and the time steps. So it can be huge, and it is why we want to use a reduced model, and we want to know how it has an impact on the output of interest. And here, what we will consider are nonlinear output to see the impact and how we can handle such nonlinear output. Okay, so the outline of my talk will be the following. So I will first present the problem statement in linear context and explain how in this linear context we can get some goal-oriented probabilistic error bands. And then I will illustrate that on a numerical example, so on the Venturi example. And then I will give some extension to nonlinear model and to nonlinear outputs. Okay, so P is the parameter space, and we consider U of mu, which is solution of that linear system. Because in all the examples I gave you, we had some continuous framework, and then we discretized. So at the end, we have a huge linear system, which can be written as follows: A of mu, U of mu is equal to F of mu. So A is the matrix of high dimension, and F of mu is a vector of high dimension. And we first consider the case of a linear output of interest. S of mu is L transpose to U of mu. Then we work with a reduced model. So I give an example, but our work is not limited to reduced basis model, but it is a way to get a model order reduction. So it's just a Galerkin projection on a reduced basis. So x tilde is a subspace of the initial space x with a dimension small n, much smaller than the initial high dimension. And Z here is just a matrix which allow to go from x to x tilde. And then we solve a projected system, so it's just a Galerkin projection. We solve a projected system on x tilde, so we solve that equation to get U tilde. So here we can illustrate that. So here, for example, the whole system is already a Galerkin projection on finite elements. So it's what we call here the true model. In fact, in that work, I'm not studying the error between the continuous model and the discretized model. And just for me, the true model is the big linear system. And here, you have a POD basis, proper orthogonal decomposition basis. So you have elements in the basis which are specified by the application itself. Here the basis is generic. Here you have a basis which is constructed from our problem. And we can say in that sense that we are looking for a meta model, that is, we are looking for U tilde in a much smaller space dimension.
Just look at, I mean, from a statistical point of view, that looks like, take Z transpose AZ over to the other side with an inverse, it looks like a weighted least squares kind of solution.
It's not exactly the case. At the end, I show an application where we do a weighted least square. Here, it is the projected system. That is, we are seeking. Not exactly the same, but
of course, and there is residual in association with the original linear system to be orthogonal with respect.
But a way to make the reduced model could be least square, or it could be Kriging. You can imagine any
just
reduced
look
model.
the formula looks familiar.
Yeah.
Yeah.
Sorry, I had a question. So the problem that you started from here, AU is equal to X. Are we talking about problems which have no time discretization in them now, or are you allowing that the discretization is both in
Yes, it's
space
both in space and time.
Yeah. But then when you talk about doing a pod basis, are you doing PV? So are you doing the pod on snapshots of a time-dependent problem?
In that case, yes, you do snapshots on. you can either do snapshots in space-time tensor basis,
Yeah.
you can do it in space and then use another scheme for time. But here in that work, our objective is not the reduced model. I just give an example, but it's rather the bound then and the output of interest.
I understand.
And so then the approximated output, it's just defined as L transpose Z U tilde, and it approximates S of mu. Okay, and so if we add some more or less technical assumptions on A of mu, so we need some coercivity, continuity, and so on, we can get an error bound on the solution of the equation itself. So we can get such an error bound. There is, of course, some work to do to get such error bounds, but you have some work with a priori error bound. But now the question is, can we deduce an error bound on the quantity of interest itself from that initial error bound? And if you add some regularity in your model, the answer is yes. For example, if you assume that your model is Lipschitz, you have this Lipschitz bound, but this Lipschitz bound is really pessimistic. And we wonder if we can outperform that bound. Okay, and we also want that our error bound is efficiently computable. So what do we mean with efficiently computable? We mean that we want to work in two phases, an offline phases, and in this phase you can make some computation depending on the high dimension calligraphical n. But then in the online phase, you do not want to use the high dimension because you want to make a lot of computations. For example, if you think about our application to sensitivity analysis, when you make the Monte Carlo estimation, you had to evaluate your output of interest many times, and you will do that during the online phase. Okay, so each time you have a sample of input parameters, you want to compute the output of interest, so you want that the cost to do that does not depend on the high dimension. So if I call C of the offline cost and C on the online cost, so it means that if, for example, if you want to estimate all first-order Sobol indices, the cheapest way to do that with the Monte Carlo approach is a cost of two capital N model evaluations. Capital N is the size of the sample for the Monte Carlo procedure. And then the total cost for the procedure will be the offline cost to design all the costs depending on the high dimension, but you do it once for all. And then you will have a cost which is the online cost, which will be repeated two capital N times. Okay, so the starting point is the following. So if you want to measure the gap between the true solution and the reduced model, usually you do not want to evaluate the true model, so you look at what is called the residual. So the residual R of mu is defined as A nu Z U tilde minus F, and it is in the high dimensional space. Okay? And then we will exploit the properties of scalar products. That is, we want to exploit the fact that if phi is element of X, the scalar product R of mu phi can be evaluated as at a cost which does not depend on the high dimension. Of course, for that, you need some properties which are classical in reduced basis models. For example, if you assume, for example, that A of mu has the half-field properties with respect to the parameter, of Q, of okay, and F of mu okay. So it's a classical property when in fact you assume that A of mu and F of mu depend on the parameter in that way. So you can dissociate the part depending on the parameter from the main part. Okay, it's a classical assumption. If it is not satisfied, it is possible to use empirical interpolation method, for example, but it is a classical assumption in reduced basis models, for example. So in that case, you can compute these scalar products at a cost which does not depend on the high dimension. So let us come back to what we are interested in. So we are interested in S tilde mu minus S mu, and it is possible to rewrite it in that way. So okay.
So I'm supposed to do that.
I don't have my formula anymore. So it is the scalar product of L with z u tilde minus u of mu. Okay, and we can rewrite it as L A minus 1 A z u tilde mu. And u of mu, because it is solution of AU is equal to F, is just A minus 1 F of mu. So now you can consider it as A minus transposed L, and then AJ u tilde of mu minus F of mu, which is nothing else than the residual. And then if you decompose A of mu on a basis of x, you get. So that quantity will be called W of mu, which is the solution of what is called the dual problem. And so. And it is exactly what we recover if I do that. So it is exactly the form we get and which makes the method work. So all starts with this quantity. So W of mu is what we call the solution of the adjoint problem. So in this linear setting, it's very simple, just related to the transpose matrix of A. Okay, and then if you want to bound S tilde mu minus S mu, you just cut this decomposition. So you use a truncation argument, which has to be designed in the following of the approach. And you will handle first the K elements here, and then you have to consider the Q of a series and see what happens. So for that term, we say that these quantities are computable at a cost which does not depend on the high dimension. So we are only interested in bounding these quantities. So to bound these quantities, we will have to solve some optimization problems. So we will have to solve 2K optimization problems because we want to minimize and to maximize this scalar product. Okay, for each phi I with I between 1 and k. And then if we define, so very simple way to bound this quantity, we define beta I up and beta I low, just taking into account the sign of the scalar product here. And we get the following bound. Okay, so we have to solve optimization problems. But that it does not depend on the high dimension. Okay, and now we are interested in the remaining part, so in that quantity. And here it is not efficiently computable. So it is why we will relax our procedure by, we will allow the bound to be violated with a small probability. So that is, we go from deterministic error bound to probabilistic error bound. And if we do that, we consider the quantity T2, which is the expectation of tau2 of mu. And we rewrite here this quantity. Okay, we control this quantity by the sum of squares, which is written in that way, where G is positive self-adjoint operator. Okay, so we have taken the expectation here. And then we get that T2 is bounded by this quantity. And if we call lambda 1, lambda 2, lambda n the eigenvalues of the operator G, and phi ig a unitary eigenvector of G, then we can minimize this bond. So in fact, what we use is a minimizing way. So sorry, we minimize the bond to get a good error for T2. And this upper bound is minimized if we choose for phi I the basis phi ig, which is the basis of the eigenvectors of G. And with this optimal choice, we get, it is an optimal choice for the upper bound. We do not know if it is an optimal choice for the true quantity of interest, but it is what we can do. And then if we optimize the bond, we get the sum of the remaining sum of the square of the eigenvalues. Okay, and it is possible to estimate phi ig at a cost which does not depend on the high dimension. And then, as I said, we consider the expectation. So what we get is not a bond, but a probabilistic error bond. That is, we accept a risk that the bond is violated. So let alpha be this risk. So alpha is between 0 and 1 and is rather small. We get that the probability that the gap between S of mu and S tilde of mu is greater than T1 of mu plus T2 divided by alpha. T2 does not depend on mu because it is the expectation, as we have seen, is smaller than alpha. And the ID is nothing else but a Markov inequality. Okay, so by accepting this small risk, and we will see that we can take the risk really small, we can get a goal-oriented error bond with a cost, with an unlike cost which does not depend on the high dimension. And in practice, we use a Monte Carlo estimation for T2, because T2 was defined as an expectation. T2 here was just the expectation of a second term. Okay. So what does it look like? So on the Venturi example, we choose the initial discretization 525 and the reduced basis, which was computed with a snapshot of size 80. The truncation argument was 20, and the Monte Carlo size was 200. And we have chosen here a risk level, which is rather small, 0.0001. So we will just consider, because I have no time to deal with the corrected output, so let us just consider the true error and non-corrected output, that is the black dot line, the true error, and the bond is the blue line. So we see that our bond is rather sharp, and we can take a risk which is really small without deteriorating the approach. Okay, and then you can estimate Sobol indices, and when you do that, so what we get here is first the confidence interval, which does not take into account the sampling error. It just takes into account the error of the meta model, the reduced order model. So you see that it's really small in that case because the reduced model does its job. And then if you add a bootstrap procedure to get the confidence intervals taking into account the sampling error, you see that you have some gap which is larger between upper and lower bound. But it is possible to get such confidence intervals. Okay. And now we are interested in nonlinear models. So what can we do with nonlinear models? So now the problem statement is the following. So M is a model from the parameter space times X into some space Y. Okay, and X and Y can be of high dimension. And we, U of mu, solve that parameterized equation, M of mu, U of mu is equal to 0. And one wants to achieve a similar formula, because we know that if we can do that, everything will be, in some sense, mimicking what happens in the linear setting. And remember that W of mu was the solution of what we call the adjoint problem. So the first question is, which definition can we take for the adjoint in this nonlinear setting? So the adjoint has to go from this space, so the parameter space times x, y, into x. And it has to be linear in the last variable in order to get this identity, because we need this identity to get this form. Okay, so we want that x1 minus x2, the scalar products of x1 minus x2 with m star is equal to the difference of f mu x1 minus m mu x2 and y. And the way we do that, we consider, we assume that m is continuously differentiable with respect to x, and then we take the derivative of m in x. And dm star is just the classical linear adjoint, and then we adapt some ideas that can be found in the literature of adaptive FEM, for example, but it is not exactly the same definition. But we take this finite different adjoint, because it is the one which does the job. We just integrate on a path the linear adjoint to get the nonlinear adjoint. And if we take that definition for the adjoint, then we get that property, and from that property we can recover this formula, which is exactly the same as in the linear setting. Okay, and now the question is, what assumptions on the nonlinearity and on the dependence in the parameter can we do in order to keep the property that the scalar products are computable at a cost which does not depend on the high dimension, because it's not so trivial in the nonlinear setting. So the solution, so we can do that with polynomial in the polynomial setting, but more generally, we get such kind of assumptions, so which look rather technical, but I will try to explain what it means. So we assume that m mu, so yi is a basis, an orthonormal basis of y, and xi is an orthonormal basis of x. And then m of mu, the sum of vi xi, has to be decomposed, is decomposed on the basis of y in this way. And what we assume is an assumption which is related to what I have written on the blackboard here. So it is some kind of affine parameter dependence, which is really classical in reduced order modeling. So that is, we assume that mj of mu v1 v capital N can be decomposed with a part which does not depend at all on the parameter, on non-parameter mu, and a part which depends on the parameter mu. So, as I said, it is already classical assumption in reduced order modeling. And then we will make another assumption, which is a sparse decomposition, but I should say we assume that the QKJ have limited interactions. So the limit of the interaction is measured by capital L here. Okay, because the V alpha here, we want that the maximum of the cardinal is capital L. That is, we want to consider only interactions up to order L. And then that assumption here, the fact that I as a cardinal which is equal to capital N, not depending on the high dimension, it is some kind of sparsity assumption. Once we have truncated the interaction terms, we also assume that we have some sparsity in the decomposition. Okay, so it's not an easy task to get some sparse decomposition of a model. There are some approaches based on tensor, for example, sparsity on tensors. But if we have such assumptions, then you can compute the scalar products at a cost which does not depend on the high dimension. Okay? If it is not possible, if you don't have such a decomposition, then the cost to compute all the scalar products will be in capital O of n calligraphic. So in that case, you will have to pay the high dimension, but it is still better than the cost if you don't use a reduced model. Otherwise, the cost is usually capital N to the power alpha with alpha greater or equal to 2. So even if you don't have such a sparsity assumption, you will pay the high dimension here, but not as strong as in the initial way. Okay. So just what I said, in that case, you have an offline-online procedure with the online procedure which does not depend on the unknown dimension. And one further comment, if the affine parameter dependence is not satisfied, you can always use some empirical interpolation, and it is what people do when they do what is called DEIM, except that their approach is devoted to Galerkin approximations. In our case, we can apply this method to any kind of metamodel, as I said, least squares, creating any kind of metamodel in a reduced space. So let us see what happens on simulation. So here I take the non-viscous burgers example, sorry. And the metamodel we used is a least square metamodel in that case. As I said, we were not interested in the best metamodel, just on the error and the output of interest once we have some metamodel. So here are the various parameters for the size of the discretization in space. It is between 40 and 80, in time between 10 and 20. Then we need a Monte Carlo sample size, here 100, the size for the POD training sample set, 70, and the truncation argument was taken equal to 8, the size of the POD basis 3 to 10, and we were interested in 2 speed-up ratio. So the first one is the full problem computing time divided by the online computing time, okay? And the second one is using the fact that we have a decomposition offline and online, for example, for sensitivity analysis. So we are interested in K. So K is not well chosen because it's not the truncation argument. It is the number of times you need to evaluate your output of interest, for example, for the Monte Carlo estimation of Sobol indices. So it's K times the full problem computing time. So it is what you will need as a budget if you didn't use the metamodel, divided by the offline cost plus K times the online cost. It is what we will have to pay with this approach.
So full problem computing time means per sample. I mean like one model run for one.
Yes, it is the cost for one evaluation of the model with the full discretized problem. So in the context of sensitivity analysis, we are rather interested by R2, but if you have to evaluate your model once, it's rather R1 that you need. Okay. And so as I said, we use a metamodel which is a list based on least squares and the POD basis. So here are what we obtain. So the first line is the full problem computing time. Then you have the online computing time, offline computing time, and the speed-up ratio R1 and R2. And here are the size of the problem we consider. So here we have a space discretization 40, and 10 and 20 for the time discretization. And here we double the space discretization to 80, and for time discretization is 10 and 20. And you see that the speed-up ratio is really interesting. And the more the model, the initial model is high, the more the speed-up ratio is interesting. And we can get, in the last case, for example, a speed-up ratio of 169, so almost 170. And here, the costs are computed using MATLAB CPU time function. And it was made on the laptop.
Sorry, if I just look at column D,
Yeah.
as the most expensive problem. So if I do it the standard way, it costs me 16,430. If I do the reduced basis approach, the offline time actually costs me significantly more.
Yeah.
So does that? So these are times per sample.
Okay, the offline-online decomposition is interested in that context.
But I mean, if I add offline and online together, it's more expensive than what you.
No, because the full time, you have to compare k times the full time. So if k is large, so here the computation has been done if you want to evaluate 1,000 times the model. And 1,000 is not a lot because for sensitivity analysis is more 10,000. But you're right, the offline phase is really bad, so high cost. But then if you have a multi-query context, it is interesting.
The K has to be big enough to see.
Yes, you have to get some application, so optimization procedure, sensitivity analysis, uncertainty quantification. And the last part, the last part is how to extend this approach to nonlinear models with nonlinear output. Because here I had some linear output because I always considered that S of mu was else the scalar product of L with U of mu. And now we will consider some more generic output of interest. So S of mu is F of V of mu. And V of mu is solution of this model. So I changed the name because you will see I will construct a new model M after that. So V is solution of the nonlinear equation H of mu, V of mu is equal to 0. And we are interested in this nonlinear output of interest. So then you can define a new quantity, U of mu, which is V of mu, and we add some dimension to this vector. So V of mu is a vector in high dimension, and we add a scalar, which is the output of interest, S of mu. So now we have a vector of size capital calligraphical N plus 1. So I will denote by overline U the first coordinate and underline U the last coordinate. And then I define a new model, calligraphical M. So the first components are just the initial model, H. And then, and the last component, I just write trivially what it means that S is the quantity of interest. That is, I write that F of V of mu, so F of overlined U, minus underline U, and we know that it should be equal to 0. Okay, so that's now U of mu is solution of M of mu, U of mu is equal to 0. Okay? And then we consider, so we want to come back to a linear output of interest by using this trick of adding a dimension. And it is the case because now we can define S of mu, it is just L scalar U of mu, with L is a vector with calligraphical n zeros and a 1. Okay, so it's just a classical trick when you add a dimension. That is, the nonlinear problem has been added in an additive dimension of the problem. Okay, so now M is still nonlinear because H was nonlinear, F is nonlinear, but we are in the preceding setting, just we have an additional dimension. And the output of interest that time can be written in a linear way. Okay, so for the illustration, I go back to the linear transfer example, so a linear model, and I will consider nonlinear outputs. The POD snapshot was 70, and the truncation argument 20, and the risk level 0.001. For a parameter mu, the true error is defined as S of mu minus S tilde of mu with absolute values. And the error band will be denoted hat epsilon mu alpha. So it depends on the parameter and on the risk alpha. And what we have plotted as functions of a reduced basis size, so I will increase the reduced basis size, that is the quality of the meta model. And what is computed is an average effectivity, which is defined in the following sense. That is, we divide on some sample of parameters, mu I. I look at the ratio of the error band and the true error. Okay, and I average on the sample. And what is also interesting to look at is the standard deviation of the effectivity. So here it's the variance of the effectivity. So it's just classical empirical variance for the effectivity. That is, we just recenter and average the square of the centering quantity. Okay, and we get that picture. I hope you can read it. So here it's the size of the POD basis. So it goes from 3 to 10. And here it's the error, which decrease. And we have no problem with the variance, because the variance is also decreasing. Okay, so here we have different graphs, because we look different. So the scale is a logarithmic scale, and we look different output of interest. So the exponential is in the middle. Here, it's for the exponential output of interest. The square is on the left, and here it's the triple exponential. So from the left to the right, the output is more and more nonlinear. Okay, so we see that the trick to add the dimension allows to handle such nonlinear outputs. So the conclusion are the following. So what we obtain, I insist, we were not interested in an error band on the reduced model. We were rather interested in an error band on the quantity of interest, which is flexible in the sense that you can work with many kinds of meta model defined on a reduced space. And we are in an offline-online setting, because we want to use this band for a many-query context, such as optimization or sensitivity analysis. And with that bands, it allows to provide some confidence intervals for sensitivity indices, which does not take into account only the sample error, but also the meta-model error. And so we have show what happens on toy examples. And what are the possible generalizations or perspectives? So, of course, here we work with toy examples, but the idea will be to go to complex models. So, for example, we considered in a previous work some work on the control of water in a channel. So we could first start with this application, because we had problem, we linearized the problem, but in fact it is a non-linear problem. And we can go to more complex models. And also, as I said, if the affine decomposition is not valid as an assumption, we can use what is called empirical interpolation method. And it will be interesting to combine this EIM and some applications with the approach I presented today. And also, as you have seen, I just consider here some variance-based sensitivity analysis, but all that stuff could be applied to more general sensitivity measures, and it will be interesting to look at the new confidence intervals for non-variance-based sensitivity measures. And here are some references. So here are the way you can derive asymptotic confidence intervals for Sobel indices. In that paper, you have the bootstrap procedure, and here is the goal-oriented error bound for linear models and for nonlinear models. And the example of Venturi was presented in the paper by Rosa and Pater. Thank you.